Greetings and welcome to lecture series on thermodynamics. Today we are starting with a new topic, air standard cycles. So before moving on to this topic, we'll see few assumptions related to this. First assumption is the working fluid is air. So air is only the working fluid which continuously circulates in a closed loop. So it will be closed system and always behaves as an ideal gas. Now let me tell you three things over here. Okay, all the three things are not true in practical. Okay, why? Because if you consider an engine, there you will have fuel as well as air. But here what we are considering, assumption is working fluid is air only. Okay, second thing, in case of actual engine, okay, let me draw the engine. In case of, suppose this is the cylinder of the engine and here you have valves. So in case of actual engine, air enters, there will be combustion process, power is generated because of which the vehicle moves, and you have exhaust also. So basically air enters in the control volume and air leaves the control volume. So actual engine will be open system, but here what we are considering, it is closed loop. So you should keep this in mind. So first assumption is working fluid is air. Second assumption is in this one only, that air circulates in a closed loop, means air is not entering and air is not leaving. Okay, your valves will not be there and cylinder will be like this. Okay, there will be piston, we will see the arrangement after, later. Okay, so this is how the system will work. Same air will be undergoing different processes. Now we are also making one assumption over here, that air is behaving as an ideal gas. Now all the processes that make up the cycles, so we will see what are the different cycles over here. All the processes are reversible. Again, in actual case this is not true. All the processes will be irreversible because there will be friction, and because of friction in actual cycle it will be irreversible cycle, and here we are assuming that all the processes in the cycle are reversible. So here you can understand from these assumptions that whatever cycles we are going to study, those are ideal cycles. Third, heat rejection and heat supply, okay, it takes place with the help of external reservoir. Okay, this point is important to understand. This we will see later. So here this is heat addition and heat rejection. It takes place with the help of external heat reservoir due to heat transfer. Next, specific heat of air does not vary with temperature. Again, this is an assumption. Okay, practically if you see, you can take any data book of thermodynamics, you will see that with temperature, specific heat of air, Cp, those values vary with temperature. But here what is the assumption? The specific heat of air does not vary with temperature. Working fluid is homogeneous throughout and no chemical reaction takes place. Now there are different cycles involved over here. So we'll see this. First four cycles: Otto cycle, diesel cycle, dual cycle, and Brayton cycle. We will be looking at the derivations and numericals. Whereas the remaining four cycles, we will be only looking at theory, the working of Stirling cycle, Ericsson cycle, Lanier cycle, and Atkinson cycle. So we'll move on to the first cycle, which is known as Otto cycle. Okay, now Otto cycle, it is an ideal cycle for spark ignition engine. What do you mean by spark ignition engine? You will find spark plug in petrol engine. So this Otto cycle, it is an ideal cycle for spark ignition engine. Okay, means petrol engine. Now why this is ideal cycle? Because we have made some assumptions like air is ideal, air is only the working fluid. Okay, then this is a closed system, that air is not entering and leaving the control volume. So air is system is a closed system. That assumption we have made. So because of these assumptions, the cycle which we are going to study, it is ideal cycle. Okay, now this cycle, it was developed in 1876 by Nikolaus Otto. He was a German engineer. So basically, to understand this cycle, what we will do is we will understand basic terminologies first. Okay, so suppose this outer part is cylinder, okay, which is hollow. So here you can see a cylinder has been shown. This is a cylinder. This is a cylinder which is empty. Okay, I mean there will be working fluid will be air only. Okay, this working fluid is air, and this part is piston. So piston is also a cylindrical, but the length of the piston is small as compared to cylinder. Okay, also, so here you can see a cylinder is there, and in the cylinder piston is there, and this piston will reciprocate inside the cylinder. And here walls have not been shown over here. So basically this is a closed system. Same air is getting compressed, same air is getting expanded. And one more thing, we have seen one assumption that heat is added with the help of some external reservoir. So I'll explain you here itself at initial stage. So here basically outside you can see over here Q in is entering the cylinder. So here what will be done? There will be a reservoir over here, attached over here, which is at higher temperature compared to internal, compared to system. So because of that, heat is supplied to the system, closed system. And similarly in this case, here you can see heat is rejected. So here heat is rejected, again here a reservoir is attached, which is whose temperature is less. So that is why less as compared to the air inside the cylinder. That is why heat is rejected, because of the gradient. Okay, so this you have to understand that air is not entering and exiting the closed system. That is why this is closed system. And the heat transfer which occurs in the system, it is with the help of external reservoir. In actual case, what will happen? There will be a valve over here and air is entering, there will be a combustion, there will be a spark, there will be combustion and heat is generated inside. Okay, but since this is an ideal cycle, we are studying this system as a closed system, and to supply heat we are using some reservoir. Now to understand this diagram, okay, I'll draw one more diagram over here. Here you can see I have kept the cylinder in horizontal position. Now why is that? Because when piston is at the rightmost position, okay, that is point number 1. Okay, then piston moves from right to left. So this process is known as isentropic compression. So from rightmost position, now here it is important to note that you have to compare these two diagrams. Okay, so these are the 4 cases. First is, here you can see on the diagram, isentropic compression is there, this one 1 to 2. Then constant volume, here you can see on PV diagram, 2 to 3 volume is remaining constant, you can see on x-axis. So this is constant volume heat addition process. This one, third process 3 to 4, this one is isentropic expansion, this part, and fourth process is constant volume heat rejection. So this is how we get ideal Otto cycle. Now here you can see the position of the cylinder is vertical. So that is why, and one more point you should note that initial position of piston is over here and final position of piston is over here. This piston, it is not touching the uppermost part of the cylinder. Why is that? Because inside air is there. right? So when you are compressing the air, obviously there will be pressure, back pressure from the air. Okay, so some clearance has to be maintained. That is why this, you can see over here some clearance has been given. So this is the end of the cylinder and air has been compressed between this one. So there are few terminologies which you need to understand. The internal diameter of cylinder, it is shown here also. You can see in the diagram, internal diameter of the cylinder, it is known as bore, B-O-R-E. And here also you can see in 3D diagram, internal diameter of the cylinder, it is known as bore, B-O-R-E. And the distance traveled by the piston. Okay, here you can see, if you are considering this top part of the piston and here also top of part of the piston, so this is the distance moved by the piston, that is known as stroke length. Okay, so here also the stroke length has been shown. Obviously there will be some gap between this end of the piston with this part of the cylinder. Okay, otherwise this will directly crash into the cylinder. Also there will be pressure increase in the air. Okay, so you need to maintain some clearance over here. So now this end, okay, this top end where the piston stops over here, this is known as top dead center. Top dead center. And bottom point number 1, where piston, again from where the piston moves up, or if it is moving from top to bottom, the end will be this one. So this is known as bottom dead center, BDC. So these are few new terminologies, like bore is there. Bore is internal diameter of cylinder. Then stroke is there, which is the length piston travels. Okay, it is known as stroke length. And the topmost position, where the piston stops, and here there will be some clearance volume. So this volume will be clearance volume, and this is known as top dead center, and this one is known as bottom dead center. Okay, it will depend on the orientation also, whether the cylinder is piston is over here or the cylinder is inverted. Okay, so these are the few notations. Now what I have done over here is we'll simultaneously see both the diagrams. Okay, we will see the top diagram also and bottom diagram also. So suppose initially piston is at point number 1. So here also you can see point number 1 piston is there. Now we apply external work. Inside the control, inside the system, what is present? Air is there. Okay, that is our assumption. And this is closed system, so you can see there is no opening in the cylinder. So air cannot escape. So piston will compress the air, piston will reach over here, and this is point 2. So 1 to 2 is, it is shown over here, this is isentropic compression. Now why this is isentropic compression? You can assume that here insulation has been provided during compression. Okay, so here insulation has been provided, and during compression heat is not rejected. Okay, so it is reversible and adiabatic. That is why isentropic. Now once the piston has reached at this position, top position, what will happen? At constant volume, piston will remain here. At constant volume, here you can see volume is constant. External reservoir is attached, which is at higher temperature, and it will supply heat at constant volume. So here you can see process 2 to 3. It is heat addition at constant volume. Now it is important to note over here that whatever points we are marking, like isentropic compression, here you can see volume is reducing. This part we have already seen in module number 1. So this module is closely linked with module number 1. All the closed system formulas which we studied in first module, closed system, for all the processes, isentropic, constant volume, constant pressure, isothermal, polytropic, all the formulas will be required over here. Okay, so we will be using those formulas over here as well. And I had already explained you how to draw PV and TS diagram. So constant pressure heat addition process, why it is vertical, I have already explained you. So you can check that. If you have any doubts, you can check that video. Okay, now we have reached, we are at point number 2. We have added heat in the system, okay, to the air. Now from 3 to 4, here you can see again it is isentropic expansion. So 3 to 4 will be isentropic expansion. Piston will move from this position, left position to right position if it is horizontal, or in this case vertical one, it will travel from point 3 to point 4. Okay, again here there will be insulation, that is why it is reversible and adiabatic, which is isentropic expansion. Now after expansion, again we attach a temperature reservoir over here, low temperature, and heat is rejected from air to the reservoir, which is Q out. So again here you can see constant volume is maintained, and this will be constant volume heat rejection. Now similarly on TH diagram, if you see 1 to 2 will be, here you can see entropy is remaining constant, and since it is compression, here you can observe that temperature is increasing since heat is not rejected. So 1 to 2 is isentropic compression. So 1 to 2 is isentropic compression, then 2 to 3 is constant volume heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection. Now obviously here also you can refer for both the diagrams why this 2 to 3 process of constant volume heat addition, it goes in upward direction. Okay, and why this process 2 to 3 of constant volume heat addition goes in this direction. This we have already discussed when we have studied the topic how to draw PV and TH diagram. So you can definitely refer that again. So this is how we have the working of Otto cycle. Now we will define some other terms also. So here you can see point number 1. I had told you before also, point number 1, this is BDC, bottom dead center, which is shown over here, point number 1. And once the piston reaches point number 2, this will be TDC, top dead center. Now we'll see the different terminologies involved in the Otto cycle. So if you consider point number 1, what is the volume of point number 1? It will be starting from 0. Okay, so from this point to BDC, this will be V1. Now V1 is equal to V4 for Otto cycle. You should remember that there are different cycles: Otto cycle, diesel cycle, dual cycle, Breton cycle, and other cycles like Stirling cycle, etc. So each cycle analysis is different. You cannot mix Otto cycle equations with diesel cycle equations. This you have to remember at this point itself. Okay, so here for Otto cycle, V1 is equal to V4. So this is not the case for diesel cycle or any other cycle. So you should remember this properly. So in case of Otto cycle, here you can see V1 is equal to V4, and then this is point number 2. So from this point, let me show you, from this 0 to this TDC, you will have V2 volume. Now this V2 volume, it is also known as clearance volume VC. Okay, this volume here I am, this is 2D diagram, but it will be a volume. Okay, it is a cylinder. So this is known as clearance volume, and wherever the piston is moving in the stroke, okay, that volume is known as swept volume, VS. It is denoted by VS. So these are few terminologies which you should remember. Now we can from here we can derive a simple formula for VS, swept volume. It will be a simple formula. What will be VS? VS is what? From point 1 to point 2, what is the volume of the cylinder? So it will be pi by 4 d square into L. What is this d? It will be bore. And what is this L? It will be this stroke. So what is the formula? So this swept volume, it will be from this point to this point. Okay, so this volume is swept volume, which is given by VS is equal to pi by 4 d square, d is bore into L. L is stroke. So this is known as, Vs is known as swept volume. Now again we will define few terminologies in case of Otto cycles. Before going for the derivation of the efficiency of Otto cycle, it is important to understand some terminologies. So first terminology is compression ratio. We are denoting compression ratio by RC. Again here it is important to note that if you refer different textbooks, you will find different notations. So we are using compression ratio as RC. It is not necessary that all textbooks are referring compression ratio as RC. Okay, meaning will remain same, notations might vary. So what do you mean by compression ratio? It is the ratio of volume before compression to the volume after compression. Now what is the volume before compression? Here you can see the diagram. What is the volume before compression? It will be this one, right? This is volume before compression. And what is the volume after compression? So after isentropic compression, piston will reach at point number 2. So this will be volume after compression. So we have to understand this. So what will be the formula of compression ratio? It will be point number 1 volume V1 divided by point number 2 volume V2. Now next definition. Now again here you can see that V1, it is made up of Vc plus Vs. Okay, so you can replace this over here. So V1 is what? This V1 is clearance volume, or V2 also you can say. So this V1 will be equal to Vc plus Vs, swept volume. So this is the total volume, which is this one Vc plus Vs, divided by what is V2? Only Vc. So this formula also you can use. Okay, so this V2 is what? Vc. Now next formula, next definition we will see. Next definition is clearance ratio. We are denoting it by K. Now what is this clearance ratio K? It is the ratio of clearance volume to swept volume. What is clearance volume? Vc. What is swept volume? Vs. So K is Vc by Vs. Okay, so same thing I have written, K is Vc by Vs. Now here you can see what is RC. Compression ratio is V1 by V2, which is equal to, we can write V1 as this also we have discussed, we can write it as Vc plus Vs divided by what is V2, V2 is Vc. So you will get equal to, so Vc by Vc you will get 1, so 1 plus Vs by Vc. Now what is this one? Here you can see, I'll highlight it. You can compare this one with this value. So here you will get equal to 1 plus 1 by K. So this is the, we are basically developing relation between compression ratio and clearance ratio. So now RC, we will take this negative side on negative on left hand side. So RC minus 1 equal to 1 by K. So K will be equal to 1 upon RC minus 1. So this is the important relation which we will be using in numericals also to solve. So this is the relation between clearance ratio K and compression ratio RC. Now next definition, expansion ratio. So now it is important to note over here that the definitions will remain same. Okay, for other cycles also definition will remain same, but those cycles are different. Okay, so the number over here might change, the formulas might change, but definition will remain same. Okay, how, that we will see when we go to the other cycle. Diesel cycle you will understand, even though there also we are defining compression ratio, definition is remaining same, but points are changing. So that is why this one formula might change. Okay, in few cases the formula might change, in few cases it might not change. Okay, we'll see in when we go to the other cycles. Okay, so this is how we get the relation between Ka and Rc. Now next definition is expansion ratio. What do you mean by expansion ratio? It is the ratio of volume after expansion. So here you can see 3 to 4 is isentropic expansion. So what is volume after expansion? V4 to the volume before expansion, which is V3. So you can write Re is equal to V4 by V3. Now in case of Otto cycle only, we can say that it is visible in the diagram that V4 is equal to V1 and V3 is equal to V2. So we can write one more formula. So V4 is equal to V1 because this is constant volume heat rejection, and V3 is equal to V2 because this is constant volume heat addition. So again here for Otto cycle, it is important to note that expansion ratio is equal to compression ratio. Now V1 upon V2 we have already defined, it is compression ratio. So this is a special case. Okay, only in Otto cycle you will find that expansion ratio is equal to compression ratio. Why? Because here we have constant volume process. So these formulas we have studied. So Re is equal to V4 by V3, Rc is equal to V1 by V2, and Re is equal to Rc for Otto cycle, and K is equal to Vc by Vs. Now we will look at the efficiency derivation of Otto cycle thermal efficiency. Very important derivation. So again I have shown over here PV and TS diagram. So basically using this diagram we can derive efficiency of Otto cycle. Now what do you mean by efficiency? We have seen this in second law of thermodynamics. What is efficiency? It is W net upon heat supplied. Okay, now since this is a cycle, here you can see 1, 2, 3, 4 and 1. Since initial point and final point is same, we can say that this is a cycle. Okay, and already it is mentioned over here that it is Otto cycle. So for a cycle, what is first law of thermodynamics? W net is equal to what? Q net. So efficiency is W net upon heat supplied, output upon input, and we can replace W net by Q net based on first law of thermodynamics. Now what is this Q net? Q net is what? You have to add whatever heat is supplied minus you have to reject, minus you have to consider all the heat rejection. So here you can see heat is supplied during 2 to 3. So QS, and heat is rejected in 4 to 1 process. So it will be minus QR divided by QS. So here you can get simplify this, you will get 1 minus QR by QS. So this is the formula of efficiency of this one, Otto cycle. Now heat is rejected during which process? Constant volume. And heat is supplied during which process? Again constant volume. So, and this is which type of system? It is closed system. And what is the working fluid? Air. And we are assuming that air is ideal gas. So which formulas now you have to use for heat rejection and heat addition? Module number 1. So here we will go to the formula list now. Okay, so I'll go to the formula list. You can see over here for closed system control volume, for closed system constant volume process. What is the heat formula? It is mCV in bracket T2 minus T1. So we will be using this formula in case of QS and QR. So we'll again go back to the derivation. So here what I have done, I am substituting what is the formula. It is mCV delta T. So instead of QR, now here you have to take when we are deriving this one efficiency, here initial stage itself I am declaring that Q value is negative. So already sign convention has been taken into account. So don't go into the details of the formula, like if you see the formula list. Okay, let me hide this. What is the actual formula here? Actual formula is Q1 to 2. direction is from 1 to 2. Formula is mCv T2 minus T1. So it has a certain particular direction. So if you see this one, when 1 to 2 is there, formula will match. But when you are going for 3 to 4, okay, so this using that formula, you will get negative answer. Okay, using this formula, you will get negative answer. Why? Because it is heat rejected. But it is important to note that we are already taking care of sign convention. How we are taking care of sign convention? At this stage itself, I am declaring that heat is negative. Here you can see I am taking this Q value as negative. So that is why when I am writing the formula of this one, heat rejection, I am not looking at sign convention. So here you can see that I am not considering sign convention. I am simply writing the magnitude. Why? Because direction, the sign I have already taken into account. So direction means I will, magnitude means I will write this as you can see over here. I have written higher temperature minus lower temperature. Okay. So 1 minus what is now the formula for constant volume heat interaction? It is mCv dt. Okay, delta T. So in both numerator and denominator, I have written mCv dt. Now since I am already taking, I am considering the sign convention of heat rejected, the formula of heat rejection which I am writing, it is rejected. Here you can see, I will highlight this in the diagram also. 4 to 1, here heat is rejected, and we have already considered this sign over here. So that is why we are only looking at higher temperature which is T4 minus lower temperature which is T1. And heat addition will be again mCv dt. Why? Because we have constant volume heat addition from 2 to 3. So again here higher temperature you can see it is T3 and lower temperature is T2. So basically we are only looking at the sign convention. We are only looking at magnitude. Okay, so this one magnitude, this magnitude we are taking, and this magnitude we are taking. Why? Because direction we have considered over here itself. Okay, there is one more way in which derivation can be done. I'll just tell you, but don't get confused. Here Q net, I can write it as Q supplied plus Q rejected. In that case, what will happen? This will become positive. This will also become positive. And since I am not taking, I am considering sign over here, then I have to, this will become positive, and then I have to consider sign in this equation. So here you will have reverse one. You can go to the formula list and check, it will become T1 minus T4. So in this way, at initial stage itself, I am taking care of sign convention, so that when I am writing the formula, I can directly see the TS diagram, and whatever is the higher temperature and lower temperature, I can write down that value. Now 1 to 2 process. So we will go process by process now. So 1 to 2 is which process? It is isentropic compression. So for isentropic compression process 1 to 2, what we can write? There is a relation between temperature and volume. What is that relation? You can again go back to the formula list. What is the relation? See this one. For isentropic process, let me highlight the isentropic process. This is the isentropic process. So for isentropic process, what is the relation? Okay, here you can see relation between temperature and volume. Okay, so respective relations can be used. So we will be using all these 4 relations throughout. Okay, wherever isentropic process is there. So again we'll go back to the derivation. So from there I have written T2 by T1 equal to V1 by V2 raised to gamma minus 1. Now we have derived this. What is this V1 minus V2? V1 upon V2. What is this term? It is compression ratio RC. So I have to substitute that value RC raised to gamma minus 1. So what will be T2? T2 will be equal to T1 RC raised to gamma minus 1. What is this RC? It is V1 by V2 compression ratio, which we have already discussed. Now we will see process 3 to 4, which is isentropic expansion. So again we can write down the formula. So T3 by T4. Okay, so T3 by T4 is, so here you should note that don't make the mistake. When T3 by T4 is there, volume is in reverse way, V4 by V3. Okay, so that you can see the formula list. So V4 by V3 raised to gamma minus 1. This formula we have already derived also in module number 1. Now, what is this V4 by V3? V4 by V3 is known as expansion ratio RE. But for Otto cycle, we have seen that RE is equal to RC. So I am replacing V4 by V3 by RC. So RC raised to gamma minus 1. So what I will get? T3 is equal to, take this T4 on right hand side, you will get T4 multiplied by RC raised to gamma minus 1. Now here you can see this T3 equation I have highlighted in red. This T3 value here also I have highlighted in red. So here you can substitute this value. Similarly, this T2 value I have highlighted in blue, and this value you can substitute over here. And if you see, compare the numerator. In numerator you have T4 and T1, and if you consider T3 value, here you have T4, and when you consider T2 value, here you have T1. Means numerator temperature and denominator temperature are matching and they will cancel eventually. Okay. So I'll substitute the values now. So again I have written the efficiency formula 1 minus T4 minus T1 divided by T3 minus T2. So I'll substitute T3 value and T2 value in this equation. So what I will get? Efficiency is 1 minus T4 by T1. I have substituted the values. T4 RC raised to gamma minus 1 minus T1 RC raised to gamma minus 1. So here you can see RC raised to gamma minus 1 can be taken common. So in bracket what you will have? T4 minus T1, and it will get cancelled with numerator. So what is the final formula which I am getting? Efficiency of Otto cycle is equal to 1 minus 1 upon RC raised to gamma minus 1. This expression is known as air standard efficiency of Otto cycle. Very important derivation. Now after deriving this, we will see how we can on which parameters efficiency depends. Okay, so efficiency of air standard Otto cycle is a function of compression ratio only. Here you can see RC is there. Higher the value of compression ratio, higher will be the efficiency. Now here you should understand. Okay, we'll see this. If this RC value is increased, means we are increasing the denominator. So if denominator is increased, this ratio, total ratio, it will decrease, and 1 minus small value will give higher efficiency. That is why it is written over here, higher compression ratio will give higher efficiency. Now I'll show a graph over here. Efficiency of Otto cycle, which is this one, given by this formula, by versus compression ratio. And here I have shown different fluids. So gamma is equal to 1.4, this is for air, and here you can see gamma is equal to 1.67, it is for this one, noble gases like helium. Okay. So here you can see different curves are there for different gamma values. Now from this graph you can few conclusions can be drawn. Okay, so what you can conclude from this graph is compression ratio cannot be increased beyond certain limit. Okay, when high compression ratios are used, temperature of air fuel mixture rises. Okay, now this we are talking about actual engine. Okay, how I understood this is actual engine? Because here it is written that air fuel mixture. Just now we are seeing ideal Otto cycle, what is the working fluid? Only air. Now this we are talking about the actual Otto cycle, okay, where we have air fuel mixture. So what will happen when compression ratio is increased? this is an interesting phenomena. Okay, understand this. So when compression ratio is increased beyond certain limit, what happens is the temperature of air fuel mixture, it rises above the auto ignition temperature of fuel. What do you mean by auto ignition temperature? At that temperature fuel will auto ignite. Okay, and because of that, what will happen? There will be premature ignition of fuel, which is also called known as auto ignition, and that is undesirable. Because of that, there will be it produces an audible noise inside the engine, and that phenomena, that noise is engine knock. Okay, so because of that, we cannot go beyond certain limit of compression ratio. Also, it can be observed that the thermal efficiency is rather steep. Here you can see the efficiency is steeper at low compression ratio, but flattens out. Here you can see after 8 it is flat. The graph is flattening. Okay, so but flattens out starting with RC of about 8. So these are the conclusions which you can draw from this graph, auto cycle efficiency versus compression ratio. So that is why here you can see that in auto cycle usually compression ratio, in petrol engine it is less. Now we'll see a derivation of work output from auto cycle. So where do you get work output? So I'll show you this in the diagram. So here during process 1 to 2, which is isentropic compression, we supply work. Okay, work is supplied to the system, and during 3 to 4 process isentropic expansion, we get work from the system. Okay, so this work will be negative and this work will be positive. Now again here you can you have to go back to the formula list for isentropic process. What is formula of work done? So for isentropic process, what is the formula of work done? Okay, it is P1 V1 minus P2 V2 upon gamma minus 1. Okay, so this formula we will be using. So here you can see I am using that formula. So for process 3 to 4, what formula I have used? P3 V3 minus P4 V4 upon gamma minus 1. Now this work is consumed. Okay, this is negative. We are supplying the compression work, so it will be negative. So minus P2 V2 minus P1 V1 upon gamma minus 1. So now what I can do? I can take this gamma minus 1 common. So here you can see I am taking 1 upon gamma minus 1 common. So inside what you will get, and again in this this part and this part I am taking P4 V4 common. So sorry, in first part I am taking P4 V4 common. So what you will get here, already I am taking 1 upon gamma minus 1 outside, and from this part, okay, let me highlight this part. From this part I am taking P4 V4 outside. So here you will get P3 V3 divided by P4 V4 minus 1. Minus. In this part I am taking P1 V1 outside as common. So I am taking P1 V1 common. So here you will get P2 V2 divided by P1 V1 minus 1. Now here I have highlighted this P3, P4, V3, V4 by some colors. Why? Because we will be replacing these values by some other value. Now one more definition I will tell you, pressure ratio, RP. Okay, definition we will see afterwards in diesel cycle later on, but just understand the formula over here. For auto cycle, what is the pressure ratio? It is P3 by P2. Okay, so P3 by P2 pressure is called pressure ratio. Now here we will do some small analysis. Process 3 to 4, if you see process 3 to 4, this is isentropic process. You can see, refer the constant this one closed system formula list. What is the relation between pressure and volume? So I'm writing that relation. P3 by P4 is equal to V4 by V3 raised to gamma. Similarly, for process 1 to 2, isentropic compression, I can write relation between pressure and volume. So that will be P2 by P1 equal to V1 by V2 raised to gamma. Now, V1 is equal to V4 and V2 is equal to V3. This is for Otto cycle. So what I can write, P3 by P4 is equal to P2 by P1 is equal to V4 by V3 raised to gamma equal to V1 by V2 raised to gamma. And now what is this V1 by V2? It is RC. And this is what V4 by V3 is what? Expansion ratio RE. And for Otto cycle both are same. So I am writing it as RC raised to gamma. Now you can understand from this that since this is in blue color, we will be substituting. Here you can see this P3 by P4. You can substitute the value over here, and this P2 by P1, this value also you can substitute over here. Now similarly we will see definition of compression ratio. What is compression ratio? It is V1 by V2 and it is also equal to expansion ratio, which is V4 by V3. So you can see it is given over here by red color, and here you can find it is inverse of this one. Here we have V4 by V3 and here we have V3 by V4. So this value we can substitute over here. Similarly, this red value we can substitute over here. So we'll substitute the values now. So 1 upon gamma minus 1 in bracket P4 V4 in bracket. Now P3 by P4 is what? P3 by P4. P3 by P4 is what? RC raised to gamma. And what is V4 by V3? It will be, sorry, V3 by V4 it will be this one. V4 by V3 is RC. So V3 by V4 will be 1 upon RC. So that I have substituted over here. Similarly, minus P1 V1 in bracket P2 by V2. I am substituting it as this is P2 by V2, which is RC raised to gamma. I have substituted over here, and this one V2 by V1 will be equal to 1 upon RC, which I have substituted over here. So now again here you can see V1 and V4 are same. That is why I have highlighted over here by green color. So this V4 and V1 are same. So I can take it as common outside the bracket, considering both the volumes are same, and I am writing it as V1. So V4 is equal to V1, and I am taking this V4 and V1 out of the bracket as V1. So V1 upon gamma minus 1 in bracket P4 RC raised to gamma upon RC minus 1 minus P1 RC raised to gamma upon RC minus 1. Now here you can see this one is 1, you can take it in the numerator, you will get gamma minus 1. So what you can write, W net equal to V1 upon gamma minus 1 in bracket P4. This one will become RC raised to gamma minus 1 minus 1 minus P1. This value will again now become RC raised to gamma minus 1 minus 1. So what formula now I can write? W net is V1 upon gamma minus 1 in bracket. I am taking RC raised to gamma minus 1 minus 1 as common. So in bracket you will have P4 minus P1. So now this P4 in this bracket I am taking P1 as common. So outside I will get W net is P1 V1 upon gamma minus 1 in bracket RC raised to gamma minus 1 minus 1. This will become P4 by P1 minus 1. So now if you remember, we have discussed this. What is P3 by P2? P3 by P2 is pressure ratio. And this P3 by P2, if you see this formula over here, let me highlight the formula. If you consider this formula is P3 by P4 equal to P2 by P1. So if you just change this one, you can write here, this P3 will remain as it is, this P3 divided by, you can take this P2 in the denominator, it will become P2 equal to, take this P4 on right hand side, you will get P4 upon, take this, this P1 is as it is, so you will get P1. So basically from this equation we can write this one. And what is this P3 by P2 equal to P4 by P1? It is RP, pressure ratio, which we have discussed over here. So P3 by P2 is what? Pressure ratio. So in this way, P3 by P2 is equal to P4 by P1. Okay, this is this equation, just we are cross multiplying, we are taking P2 over here and we are taking P4 on that side. So you will get pressure ratio. So now you can write down this equation in terms of pressure ratio. So a final equation of work output from Otto cycle, what is the formula? P1 V1 upon gamma minus 1 in bracket RC raised to gamma minus 1 minus 1 in bracket this P4 by P1, it will become pressure ratio RP minus 1. So this is the derivation of W net. Now next important definition we will see, mean effective pressure. It is denoted by MEP, mean effective pressure. Now in numericals also you have to calculate the value of mean effective pressure. So understand the concept of this mean effective pressure. So what is done? It is a fictitious pressure that if it acted on the piston during entire power stroke would produce same amount of net work as produced during actual cycle. So here you can see 1 to 2 is isentropic compression, then 2 to 3 is constant volume heat addition for Otto cycle, 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection. So if you constitute this cycle, what is the W net? It will be power produced during 3 to 4 minus power consumed during compression from 1 to 2. That is W net. So this you can replace by a horizontal pressure. Okay, so this will be a pressure like this, horizontal pressure, such that, so it is a fictitious pressure that if acted on the piston during the entire power stroke would produce same amount of net work. So if you consider area under PV diagram is what? Net work. So what will be this one? Area, it will be this area of rectangle. Area of rectangle. Okay, so let's see the definition of this one. So mean effective pressure is W net upon swept volume. And what is the definition? It is a fictitious pressure, okay, imaginary pressure, if it is acted on the piston during the entire power stroke would produce same amount of net work as produced during actual cycle. So a mean effective pressure is net work output upon swept volume. Now net work output formula we had just derived, this formula W net in the previous slide. So that value we have to substitute. Okay, so we'll see that now. Now what is the swept volume? Swept volume, see this diagram, swept volume, it is this one, Vs, which is from V1 to V2. Okay, it is from V1 to V2. So what you can write? V1 minus V2 is equal to Vs. So this swept volume means what? It is Vs. So this is equal to V1 minus V2. So we can take V2 common. So you will get V2 in bracket V1 by V2 minus 1. And what is V1 by V2? Compression ratio RC. So equal to V2 in bracket RC minus 1. Now substitute this value of the, in this equation. So mean effective pressure is, this one is W net value which we derived in the previous slide, this one W net value, and this value is the swept volume. So here you can see, if you consider this one, I'll just give you for some understanding, I'll discuss this formula, how we get this formula. So what is area under PV diagram work, na? So this W net is equal to, if you take this swept volume on left hand side, what you will get? So it will become mean effective pressure multiplied by swept volume Vs. So it will be like this. So it will be rectangle like this. Okay, this extra part will not be there. Let me clear this. So this rectangle, suppose this is the rectangle. So it will be area under PV diagram is work done. So this will be work done, and this W net will be mean effective pressure, which will be this one. This pressure will be mean effective pressure. If you extend this horizontal on the y-axis, you will get mean effective pressure divided by swept volume. Now what is this V1 by V2? V1 by V2 is what? Compression ratio. Now you can replace this V1 by V2 using this compression ratio. So final formula of mean effective pressure which I am getting is P1, and V1 by V2 will become compression ratio in bracket RC raised to gamma minus 1 in bracket RP minus 1 bracket complete, divided by this gamma minus 1 is in the denominator, so gamma minus 1 and RC minus 1. So this is the formula of mean effective pressure. Now after this I'll show you the formula list. So this formula list will be given to you. So understand the formula list. Here I have written Otto cycle PV diagram has been shown, and all the definition here you can see clearance volume will be Vc, which is equal to V2 equal to V3. What is V1? V1 will be Vc plus Vs. Then clearance ratio, compression ratio, expansion ratio. I have written over here expansion ratio is equal to compression ratio for Otto cycle only. Then all the if you consider process 1 to 2, which is isentropic, and process 3 to 4, which is again isentropic, I have written all the relationships: temperature pressure relationship, temperature volume relationship with respect to compression ratio, then pressure volume relationship, and from here we get some other parts like this P2 by P1 is equal to RC raised to gamma, and P3 by P4 is also equal to RC raised to gamma. So we can find that P2 by P1 equal to P3 by P4 as we have seen in the derivation, and RP becomes equal to pressure ratio is equal to P3 by P2 equal to P4 by P1. This already we have seen, okay, in the derivation. And this type of if you consider process 2 to 3, this is which process? Constant volume process. So when volume is constant, what is the relation between pressure and temperature? These are the two relations: P3 by T3 equal to P2 by T2, and P4 by T4 equal to P1 by T1 for 4 to 1 and 2 to 3. So this you can find in the formula list. Okay, let me show you the formula list. For constant volume, what is the relation between pressure and temperature? It is P by T is constant. You can say volume is constant. So you will get P1 by T1 equal to P2 by T2. Using that, here you can see P2 by T2 equal to P3 by T3. So same thing I have written over here, this one. And similarly, when I am writing small qs, so this is per kg mass. So I am not writing m, and since heat is added and rejected at constant volume during process 2 to 3 and 4 to 1, this formula we had seen in derivation, it becomes CV T3 minus T2, and this formula becomes CV T4 minus T1. Now you should note that this formula T4 minus T1, okay, this here sign convention is not taken care. So when you are using this Q rejected, you have to use a negative sign separately. Okay, and this formula we will understand when we are solving the numericals. So we will go to this. So all the formulas are given. The mean effective pressure formula is given over here. Okay, some more mean effective formula is given over here. I will be providing you this PDF file of formula list. You can go through this formula, how we arrive at this formula. Okay. Now we'll see a small numerical. Okay. This is independent of our topic. Okay. It is not related to air standard cycles or gas power cycles. It is related to pressures. Okay. So a very interesting question has been is there. Okay. So please pay attention. Very easy question, but very tricky question. And we will learn about a new concept over here. Okay. So just understand the data. Volume and temperature of air. Air is assumed to be ideal gas and ideal gas in a closed vessel. So this is a closed system and volume is 2.87 meter cube and temperature is 300 Kelvin respectively. Gauge pressure. So here you can read a new terminology has been used. Okay, we have not seen this. Gauge pressure. Indicate by a manometer fitted on the wall of a vessel is 0.5 bar. If gas constant R value for air. Now here you should note what we have considered R value as 0.287 kilojoule per kg Kelvin. Here R value is given in joule per kg Kelvin, which is 287 joule per kg Kelvin. Okay, so don't get confused. You have to see the units properly. And atmospheric pressure is 1 bar. Now here what we have to calculate, the mass of air in kg. So this is easy. Why it is easy? Because here three data are given. This is volume is given, temperature is given, and pressure is given. Two different pressure values are given. So what equation we will use? PV equal to MRT. PV equal to MR into T. But the problem is which pressure to take. We have two pressure values. One is gauge pressure and second one is atmospheric pressure. So how to solve this? Here you will understand a new concept. Okay, so we'll see this diagram is shown over here, which indicates different types of pressure. So here you can see the lower pressure value. This pressure is absolute zero pressure. Means here the value of pressure, P value is 0. This is absolute pressure. Now, if you consider pressure gauge, okay, you might have seen there is a pressure gauge like this. A shaft is there and a dial is there, and this shows pressure value. Okay, it is this type of pressure gauge. It is attached in a pipeline. Okay, it is attached in a pipeline whose pressure has to be measured. This pressure gauge, it gives gauge pressure value. Okay, so here you can see this gauge pressure. This gauge pressure is given by this pressure gauge. Here also you can see vacuum is there. This vacuum is also given by this pressure gauge. There will be different type of pressure gauge in that case. Okay, that is why these pressures are known as gauge pressure. So here you can see I have shown atmospheric pressure. Above atmospheric pressure, whatever the value of pressure we get, it is known as positive gauge pressure. And below atmospheric pressure, whatever the gauge pressure we get, that is known as negative gauge pressure, and it is called vacuum. Now, if you are measuring the pressure using pressure gauge, how to get absolute pressure? Now, in the equation PV equal to MRT, PV equal to MRT, this equation, whatever pressure is there, this pressure is absolute pressure. Okay, and we have been given atmospheric pressure and gauge pressure. So how to get this one? This is, see, this pressure is 0.5 bar, means it is positive gauge pressure. So how to get absolute pressure? Absolute pressure will be atmospheric pressure, means up to this point. Okay, see, now this is atmosphere, and this is positive gauge pressure. So this much gauge pressure is shown in the pressure gauge. Okay, this gauge pressure is shown by this manometer. So what will be the absolute pressure which we have to substitute in the equation? It will be atmospheric pressure up to this point plus gauge pressure. Okay, when we get the negative pressure, in that case, what will be the absolute pressure? Here it is written absolute pressure when less than atmospheric pressure. So when vacuum is there, when negative gauge pressure is there, so what will be the formula? It will be atmospheric pressure minus gauge pressure. So you have to understand that gauge pressure can be positive or negative, and when we want to convert it in absolute pressure, if gauge pressure is positive, we need to add atmospheric pressure value. If gauge pressure is negative, we need to subtract gauge pressure from atmospheric pressure. Since in this question gauge pressure is positive, what will be the formula of absolute pressure? It will be atmospheric pressure plus gauge pressure. So here you can see now the solution. Volume has been given, temperature has been given, gauge pressure is given, atmospheric pressure is given. So what will be the absolute pressure? Okay, forget about this. Here there is a here it will be addition. So this will be gauge pressure PG plus atmospheric pressure. So gauge pressure is 0.5 plus 1, you will get 1.5 bar. Now PV equal to MRT. PV equal to MRT. In this equation, what is P value? It is 1.5 bar. So 1.5 you can convert in kilopascal. So 1.5 into 100 multiplied by what is the volume? Volume is 2.87. 2.87 equal to M value we have to calculate. And what is R given? R is given as 287. We use R value in kilojoule per kg. So it will become 0.287 multiplied by what is the temperature given? 300 Kelvin. So multiplied by 300. So using this equation, you will get value of M, and M is coming out to be 5 kg, and answer will be C. Now, one more thing I will like you to observe over here. This is an important concept. In this case, when we have discussed this, when we are using PV equal to MRT, we use pressure in kilopascal. In that case, this R value we have to use in kilojoule per kg. Okay, but instead of this, we can follow other system also. So in this case, instead of substituting in bar, we can substitute in Pascal also. So here you can see pressure value has been substituted in Pascal. So how to convert bar into Pascal? It will be 10 raised to 5. So 1.5 into 10 raised to 5 Pascal multiplied by volume is 2.87 divided by, now here you can understand, here we have taken, when pressure is in kilopascal, we are taking R value in kilojoule per kg Kelvin. But when pressure is in Pascal, we have to take R value in joule per kg Kelvin. So that is why here it is divided by 287. Let me clear this. It is divided by 287 multiplied by temperature. So both the methods are valid. Either you can keep pressure in Pascal. In that case, R value you should remember to substitute in joule per kg Kelvin. But whatever numericals which we have solved in thermodynamics, according to that we are solving taking pressure in kilopascal, volume in meter cube, R in kilojoule per kg, and T in temperature.